Welcome student to our wave optics course. So, in the last class we developed the concept of interference and then introduce how the double slit will work, and then also we introduce that there are few other techniques through which you will going to get the interference pattern, namely the Lloyd's mirror experiment and also the Fresnel's biprism, where using these two instruments you can manage to get the interference pattern. However, there are other technique also. So, in today's class, in lecture number 19, we are going to discuss about the interference by division of amplitude. So, let me start with that. So, today we have lecture number 19. And this is lecture number 19, and what we are going to study is interference by division of amplitude. So far, in the case of Young's double slit experiment, what we had a system like this. We have two sources here, or two holes, A and B, and then from one source, this is the wavefront that was there, and then from A to B, two separate wavefronts were generated like this. And throughout the process, what happened, that they interfere at some point on the screen, say P. So, here we have the division of wavefront, because wavefronts are divided. So, we have division of wavefronts. In today's class, however, we will try to understand that what happened instead of wavefront division, we have amplitude division, and how it happens. Let me give you a very simple example here, that suppose you have a single film, and if light fall on that, then one part will be refracted and one part will be reflected from this point. This is ray number 1, which is reflected, and this ray which is refracted will again reflect from this point and get refracted like this. This is ray 2. So, I have ray 1 and ray 2, and essentially they can, if I put a screen here, they can interference with themselves. Now, this ray 1 and ray 2, the interference that is happening due to ray 1 and ray 2 is due to the division of amplitude, because here the amplitude get changed. In this 1 ray and 2 ray should not have the same amplitude. So, that is the basic structure one can have when they try to understand how by division of amplitude interference take place. So, this is due to division of amplitude. From this figure, it is also clear that the ray that is traveling, ray 1, directly from this point, and the ray that is traveling from this point, which is going through the film, So these two rays should not have the same path, because there is already a path difference that is encountered by this ray 2 during this process. So if somebody calculate the path difference and then calculate what is the path difference, then like the previous case, the path difference will determine whether these two interference will going to get a maxima or minima at some point. So that we are going to check today, that what should be the calculation, what should be the path difference in terms of these parameters. Suppose this is having an refracted angle phi t, and the thickness here is t, and the refractive index is f. With these three parameters, we try to find out what is the path difference. If these three parameters are given to you for any kind of structure having this form, essentially one can find out the path difference. So let us do that in the next page. Okay, so this is single film interference due to single film. So single film interference. Okay, so in order to find out the path difference, I need to draw it once again. So let me draw it, exactly the same figure I am going to draw. This is the ray that is falling here, and then it is refracted, and it is bounced back here, and then again go to this direction. On the other hand, I have one ray that is going this direction after reflection from this surface. So I have this. Now let us consider this angle to be incident angle to be theta I, and this angle to be theta t, transmitted angle. Refractive index here, say NO, and refractive index of the film is NF, and also the thickness that I mentioned is T. Now I need to find out the path difference. So let me first write down. So this is A, this point is A, suppose this is B, leading point C, and if I draw a perpendicular here, then this is D, and this angle is easy to show that this angle should be theta I. Note that this theta I angle and this angle, whatever the angle, say x, is pi by 2, because this is 90 degree, and this angle and this angle theta I is also pi by 2. So from that it is easy to show that this angle should be theta I, the incident angle. Well, if I draw a perpendicular here, why I am doing that I will explain. There are several ways through which you can find out the path difference. I am just showing one of them. And if you draw a perpendicular here from this point, so this is, say, point G, this point is E, and this point is F. So, the optical path difference, let me calculate here based on this figure. So, light is falling here, reflecting back. So, the optical path difference delta is equal to the extra path that is traveling. This is ray 1 and this is ray 2. The extra path traveling by ray 2 that we need to calculate, which is this AB plus BC. So, NF multiplied by AB plus BC, and then this path AD, that is the additional path that is traveling by ray 1. So, that I need to subtract. So, minus NO multiplied by AD. So, that is the path difference between the ray ray 1 and ray 2. So, I can split this in this way for simplicity of the calculation. So, let me write down delta is equal to then NF AB, I define AE plus EB plus BF plus FC. I just split this AB and BC in this way, that is one part here AE plus EB and BF plus FC, then minus of N naught AD. So, that is my path difference. Now, I need to put some kind of geometry to find out what are these values in terms of NF, theta t and t. So, let me write here sine of theta t. By the way, let me find out what is this angle. This angle is, this is theta t, this is theta t minus 90 degrees. So, this angle has to be theta t. Similarly, this angle is also theta t. So, let me write it clearly. So, angle AGE is equal to angle FGC is theta t. Very easily one can check that. So, sin theta t in that sense should be AE divided by AG, or AE is equal to AG of sin theta t. Now, by symmetry we can write AG is equal to AC divided by 2. So, essentially I have AE is equal to AC divided by 2, then sine of theta t. Okay. Now, we also have AD, which is here to here, and this angle is theta I, is equal to AC into sin theta I. Now, from the Snell's law we have N0 sin theta I is equal to NF sin theta t, just using the Snell's law. So, if I calculate N0 AD, then let me write down, if you calculate this thing, N0 AD, that is the last part of this part difference, this is 2 of this AD, I am writing 2 of NF AE. Why it is that? Let me check. Because let me do that in this way. So 2 of AE from here, from this equation, I get this is equal to AD sin of theta t divided by sin of theta I. AD sin of theta I, AD divided by sin of theta I is AC, and this is, so here I have 2 of AE is equal to AC of sin of theta t. So that AC I write from this equation, I write AD divided by sin of theta I, AD divided by sin of theta I, that is 2 of AE. So this quantity I can write AD. From the Snell's law, I just use this is N0 divided by NF. Okay. Now also we have cos theta t is equal to EB, cos theta t means this is EB by GB, because this angle is theta t. So cos theta t is EB divided by GB. Now this GB is nothing but the thickness. So our aim is to find out everything in terms of thickness T, theta T, and the refractive index NF. So this quantity will be simply EB divided by thickness T. So that we know. Now let me go back to the equation that we had, delta equal to NF AE plus EB plus BF plus FC and then N0 AD. N0 AD I already calculate, this is NF into AE, and this AE means this to this. Now AE can be, this 2 of AE can be written like NF multiplied by AE plus FC, because AE and FC are same. So this I can write is NF multiplied by AE, 2 of AE, I write AE plus FC. Now all the components I believe I figure out, I need to put it here. So if I do that, then my delta is equal to NF, then EB plus BF, that is equal to 2 of NF EB. So EB plus BF means this is EB and BF. EB and BF, they are same. So 2 of EB is EB plus BF. In a similar way, I can write EB plus BF is equal to 2 of this EB. Now that quantity is equal to 2 of NF of T of cos theta T, because you remember that cos theta T here, it was EB by T that I calculated here. So cos theta T was EB divided by thickness. So EB I can calculate in this way. So the path difference finally we can have this quantity, because rest of the quantity is cancelling out. So here if I see that this quantity N0 AD was NF AE plus FC, and NF AE plus FC was already there. FC is equal to FC and AE, this quantity is here. So I can write it as, so let me write it once again here. So I can write NF multiplied by AE, this, and FC from here plus FC, that is one part, then plus NF EB plus BF, that is another part, and then minus N0 AD, that was the value. Now N0 AD I calculate, which is NF AE plus FC, which is a negative sign. So this term, these two terms, NF AE plus FC and N0 AD, they are same, so they will cancel out. So these two term, mind it, these two term will cancel out. So these and these are same. Rest of the term is NF EB plus BF, and that essentially we calculate in the next plate, NF EB plus BF, which is equal to NF 2 of NF T theta T. So finally the path difference, let me draw once again. If this is my structure, single film, rays falling here, this, then if this thickness is T, this angle is theta T, and the refractive index of the film is NF, then the path difference difference between ray 1 and ray 2, the path difference between ray 1 and ray 2 delta is simply equal to 2 of NF, then thickness T and cos of theta T. So that is the path difference we have, and note that when the ray falls normally, then theta T value is 0. So we can have for normal incidence of light, theta T is 0. So the path difference will be simply 2 of NT into T. The optical path difference will be simply this quantity. But there are couple of things that we need to know here also, and that is the reflection. Due to the reflection, the additional phase shift occur, and this additional phase shift is of the amount of pi. So an additional phase shift is arising from the reflection. So that means if this is N1 and this is N2, we have a pi phase shift and this pi phase shift occur when it is reflected from denser medium to rarer medium. So in this case N2 be greater than N1, and we will going to get a pi phase shift here, that we need to consider every time. So what is the condition for constructive and extractive interference? Let us quickly now check. The phase difference obviously lead to a path difference, this phase difference pi. So for the phase difference pi due to reflection leads to a path difference I write delta R of lambda by 2. This path difference arises solely due to the fact that light is reflecting from N1 medium to N2 medium, and this N2 medium is higher than N1 medium, the refractive index N2 is higher than N, and this case pi phase difference is there. So if there is a pi phase difference, there should be a path difference, associated path difference that we need to consider, and that is lambda by 2. So the total path difference will be defined by the path difference due to the ray that is passing through this film that we calculated 2 nt t cos theta that we calculated, cos theta t, but you need to add an additional path difference with that because of this reflection issue. So, that should be the total path difference. Now, for constructive interference, we can have the path difference delta plus delta r to be the integer multiple of lambda, and for destructive interference we have the path difference delta plus delta r is equal to m plus half lambda. So, with that note, today I would like to conclude. So, what we have learned today is that in the previous class we understand that when two waves are interacting through this double slit experiment, then there is a division of wavefront, and because of that interference is happening. There are other conditions also to have the interference, and the conditions are they should have these two beams should have coherence in nature. However, also one can have this interference by using this division of amplitude method. In the division of amplitude, what happened? If the ray is falling over a surface, a part of the ray can be transmitted and it can again reflect to the second boundary and then come back. Also, another ray that is transferring from the surface of this interface is there, and these two rays will going to interfere. This interference is happening because of the division of amplitude. Here the amplitude is divided, and we will find that because of that there is a interference that is happening. And also the condition that we need to take care here, that when there is a reflection, because of that a pi phase difference occur every time, and this occurs when the refractive index N2 is higher than N1. So, N2 is higher than N1. So, that condition gives us an additional path difference lambda by 2. So, during the calculation we need to take account these facts. So, with that note I would like to conclude here. So, thank you very much for your attention, and see you in the next class, where we are going to learn more about the interference due to division of amplitude. Thank you very much. See you in the next class.